Supercomputing, the gateway to AI. That's the title of this conference, I guess. So when you hear this, there are two questions. One is, how do I get access to this, which is what Per has been talking about and what we'll hear later after me as well. I will talk about a different question, and why should you want this? So I work at a compute cluster, and I will talk a bit about what our users have been doing there. But first, a bit about the cluster and me. The cluster is from 2020. It had a huge upgrade in 2022. It was financed by Knut and Alice Wallenberg Foundation. Operations are paid by SNCC, and now it's taken over by NICE, and it's hosted by Chalmers University, where I work. We're small in this setting. It's hard to say that a computer is small when the electricity bill is comparable to the cost of 5 PhD students. But it's smaller than Lumi, at least. For me, I started working here in 2021, so I've seen most of the lifetime of this system. And I helped our users then, our researchers, use this system. As a requirement by the founders, it's only for academic use and only for AI and machine learning. I'd also like to thank my colleague, Sahar, who is not here today, who helped me with some of the research for these slides. This is what I based it on. You can get an interactive version of this in the link, because it's probably hard to read. For each project that are using this cluster, you have to specify what is the classification, what they're doing, and the title and an abstract. And then additionally, after they've done, they have to submit activity report on what they've done. Based on this, I did some manual clustering, and this is about the topics they're covering. So vision is still a large share of the research that is being done. I split it up into passive things and active things. Then we have approximations, which is kind of a vague topic, but I'll go into it more. It's basically when you have something you can already do, but you want to do it cheaper, faster, or other things. We have, of course, improvements to machine learning itself, as it's a research cluster, so we have basic science on machine learning as well. Sequence data, of course, text, code, bioinformatics, and then I'll talk a bit about inverse problems and generative AI. So for vision, for these slides, you'll have some titles of different projects, and then on the right side, you'll see some images that are perhaps more easily to look at. So for vision, we have a lot of different applications. Medical imaging is a big one. You can have medical imaging for X-ray, MRIs, CT scans. There are different challenges here. So for example, CT scans, it's no longer just 2D data. You can have volumetric data here as well. You have, of course, other types of object detection, or here's one example of facial recognition in historical photos. And then, of course, we have microscopy. Microscopy is a big one. If you look at the list of Nobel Prizes, you'll be surprised at how many of them are about microscopy. This one in particular is a scanning electron microscopy, which is my favorite microscopy method, just because they look so nice. But here you have the different challenges. It could be pixel level identification of different things in the slides. And in particular with microscopy, the data is scarce and it's expensive, because you have someone with high education that has taken a lot of pain into producing these microscopy images. So you have to work with the data you have. We've seen other examples here in the industry where data is limited, and what can you do about leveraging other data or modifying this data to work with it. Satellite imagery, we've seen a few different applications. So one is looking at the economic state of different areas in third world countries to kind of better direct aid efforts. But we've also seen predicting droughts, tracking wildfires, so these kinds of things. On the active side, we have autonomous driving and robotics. So of course, beyond just the vision part, you have the active part of taking actions, having a policy for based on what you see. But also on the vision part, there are new challenges. So the lenses can be different. So here you see a fisheye lens. The typical assumption in convolutional neural networks that things will look the same no matter where you are in the image doesn't hold here. So we have research on this. What other symmetries can we use? And then we also have LiDAR data. So this is entirely different from images. Here you get a point cloud instead of pixels. Moving on, for approximations, this is a wide variety of things, but we have seen a lot of use for material science, where they replace a part of calculating the electronic potential, the force from the electronic potential, and replace this with deep learning. We heard from AstraZeneca yesterday that this was not quite good enough for them, but we've seen a lot of use, at least in material science, and it's a growing field. But you can also do this for other things. So we've seen in computational fluid dynamics, replacing some parts with deep learning. These are fields where have been using HPC for a long time and using a lot of HPC. But now we're seeing them replacing some parts with deep learning, just to speed up the computations and doing even larger things. I included one example here from medicine industry because I felt it was interesting. So they had already screening methods for some drugs, but this was very limited and couldn't screen everything. So they basically did some interpolation on this kind of, and this later turned into a commercial application, and they started a company. On improvements to machine learning, here we have a lot of different things. It can be multimodality. We've heard about this. This is about combining different modalities. So this could be text, images, sound, but also methods to better train networks. So we have better looking at the different hyperparameters. What are the settings you can use when you train them, and better choosing this. Here's an example with Bayesian optimization. It can also be federated learning, about learning, but not in one center. So instead of sending data to one place and training your networks, it's about learning on the edged machines and then sending the updates to a central location and then aggregating the updates and sending it out. But it's also other things like looking at the geometry of the loss landscape or models, looking at explanations of models, and so on and so on. Sequence data is a big one, especially now with large language models. So of course you have ways of turning text into something that's more suitable for machine learning. So it's some way to turning this into continuous numbers or floats. But then you can use these methods as well, not just for text, but also for code, of course. That's one type of text. You can use it for different word equations. So this is kind of data set queries and so on. And then you can also do a lot of things with these types of text. Another area where you have this type of sequence, that's bioinformatics. So a protein, that's a sequence of amino acids. So that's also a discrete set of things you can have. And then it's a sequence of them. So you can use the same methods. Transformers is large in this space. We have, of course, the AlphaFold, and AlphaFold 2 in particular, that is large. We have a few groups that have been using that. This is about turning a sequence of these amino acids and telling what does the protein look like. Because a lot of the functionality in the protein comes from the shape of the protein. So this is protein folding. But that's not the only thing you can do of this data. If you don't, in particular, need to know the shape, you can look at what other aspects can we get from this type of sequences and directly do some inference on it. Other types of sequence data we have is, for example, chemical structures. This is more of graph-like. So you have graph-based neural networks as well. But you can also do something with sequences. For audio data, we don't have that much, actually. I'm not sure why. We have a few. So here's one where they looked at the sound of someone breathing and could say, well, do a diagnosis based on this? So for inverse problems on generative AI, so generative AI is really big nowadays. So this is ChatGPT, DALL-E, and all of these. For inverse problems, we have the structure of, you have something where you can tell in one direction easily. So perhaps you have a material, and then you have a way to calculate the properties of this material. But what you would like is tell, I want a material with these properties. What material is it? So then you can train a network to kind of do the inverse of this. We've also seen applications here to kind of better sampling efficiency for computed tomography, CT scans, because that's also a type of inverse problem. We have seen a few different ones. On generative AI, we have not seen really big large language models. As we saw from AI Sweden, you need really large resources, and that's probably why. We had 880 GPUs. Half of these are about A100s and half are A40s. So if you want to train a neural network, only half the cluster is available, basically. So that's too small for the large language models. What we have seen is fine-tuning on these. So that's something we've seen a lot, lately at least. But for generative AI, you have the structure of, you have something that generates something, and then you have a way of telling, does this look like what you want it to look like? So you have some data set you want to kind of have something generate things like this data set, and then you have some way to tell, well, is this similar or not? So typically you have two networks, one that generates and one that discriminates and tells, was this generated or was this an actual image from the data set? And then you train them in tandem. For large language models, it's simpler than that. You have something to predict the next token, and then the simple way to tell whether it was a correct prediction of the next token or not is the actual token that will come later. Looking at all of these different examples, I'll try to help you answer the question of how much compute will you need. So the axes here are deliberately vague, so I could have this kind of plot. So complexity could be how hard is your problem to solve, especially the data you have, what's the structure in the data, and how hard of a task do you want to solve. And then the harder it is, the more compute you will need, basically. So for classical machine learning, you could do simple things like linear regression or simple clustering. It doesn't need that much compute, but the data needed to be structured quite nicely. And what you could do was quite limited. But then when we come into deep learning, you have methods of looking at images that are unstructured, but then you can learn a lot about one image data set. And then the network has learned a lot of properties like finding edges, finding curves, and similar things. And then you can use these features in transfer learning or feature extraction, and then apply this to simpler methods. In the high end of compute and complexity, we have the large language models or general models, foundation models, where you train on very, very large amounts of data. They can do complex tasks in the sense that it covers quite general scopes of things, but you require a lot of data and a lot of compute. And then to leverage this is the fine-tuning. As I mentioned, we don't have those that have trained large language models on our cluster, but we have a lot of people fine-tuning large language models for their use cases. So with this, I hope you have a better sense of why you would perhaps like to have more compute.
Thank you, Viktor.